This is questions 7 and 8 from the Integral Maths topic test on kinematics. With question 7, we have a ball thrown vertically upwards with a particular speed from a particular point, and then 3 seconds later, a second ball thrown vertically upwards from the same point with the same speed. So the only difference is the 3-second delay. We're told we can use acceleration as 10 meters per second. We need to work out the two key things: when the balls meet, in other words, when their heights are the same, and the height that they are at when they meet. So we start with this key idea. Think about a value t. I've called it capital T so as not to confuse it with the lowercase t that we've got as one of our SUVAT variables. If capital T is the time for which ball A has been in flight, then we can use capital T minus 3 for the time for which ball B has been in flight. And then the two SUVAT equation setups look very similar. We have an initial velocity. I'm treating upwards as positive, and therefore acceleration is negative. And this one has the same upwards velocity of 25 meters per second, and it has the same acceleration downwards of 10 meters per second. The only difference is that t is equal to capital T minus 3. So when we apply s equals ut plus half at squared, we get two similar looking but subtly different expressions. And the key thing here is that the balls will meet precisely when they're in the same place at the same time. In other words, when these two displacement expressions are equal to each other for a particular value of capital T. So we solve simultaneously. We set SA equal to SB, and we end up with an expression on each side which is quadratic, and yet because they were fired with the same initial speed and they're under the same acceleration, we find that quite a few things cancel out, and the quadratic equation reduces to a linear equation, which suggests that there is only one moment in time when these two will be at the same height, which kind of makes sense because they're tracking each other. It's as if one of them is the other one in the past, or the other one is this one in the future. So there is only one moment when they happen to be at the same height at the same time. That works out to be 4 seconds after the first ball is thrown up, which will be equivalent to 1 second after the second ball is thrown up. And if you think about it, that suggests that the second ball is on its way up and the first ball is already on its way back down. And if you substitute back in, you can work out that this happens when they've moved to a displacement of 20 meters. That means the one that's just reached a height of 20 after 1 second has only moved 20 meters. The other one has moved all the way up to its highest point and then come back down to a displacement of 20 meters. It's covered a greater distance, but its net vertical upwards displacement is 20 meters. A good way to check this is to substitute into the other formula for SB and see if we get the same 20 meters. And that seems to work fine. You can also use the symmetry of this situation to do another check. Because a ball thrown at a speed of 25 will reach a height of 20 after 1 second and again after 4 seconds, exactly halfway between those 2 points will be the moment when it reaches its highest point. And you could substitute that into v equals u plus at, and it gives you 25 plus negative 10 times 2.5, and that gives you 0. In other words, the speed in between those two moments is 0, which makes sense because at that point, the ball would be, at least for a single instant in time, completely at rest. Question 8 is a similar situation where we've got two particles, in this case cars, traveling in the same direction along a straight road. And at the very beginning, we know that the car A is at rest, it's not moving, but it accelerates at 3 meters per second between 0 and 10 seconds, then travels at a constant speed. Car B does something a bit different. It's already traveling at 15 meters per second, about 30 miles an hour, throughout the first 30 seconds, and then it accelerates at 1 meter per second until it reaches a speed of 25, after which it continues at a constant speed. A good method for creating a velocity time diagram is to find checkpoints along the way. Think about any points where the acceleration changes, because when the acceleration is constant, we have a straight line. And if we have a different constant acceleration, we'll have a different straight line. But in between, there'll be a point when the slope of the line changes. So I've started by writing down my checkpoints. Car A starts out at 0, 0, because it starts from rest. It accelerates at 3 meters per second between 0 and 10, which means it has 10 seconds of 3 meters per second acceleration, meaning its speed is going to increase by 30 meters per second. and that takes it to a speed of 30 meters per second because it started from 0. So I've got the point 1030. I can calculate directly from that. The numbers are nice enough to do this in your head, but if they get messier, or if you want to be more sure of yourself, you can calculate this using v equals u plus at. And the last bit, I've decided to use 80 for my final point because it says sketch the motion between 0 and 80 seconds, but you can use any arbitrary big number for this one because it says that the car continues at a constant speed. So no matter how far we go now from this point onwards, we're going to still have a speed of 30. Car B is a bit more complicated. It starts out already going a speed of 15, but it has a constant speed for the first 30 seconds anyway, so it's still going 15 after 30 seconds. And then it accelerates until it reaches a speed of 25. So we need to figure out how long that takes. But if the acceleration is only 1 meter per second, to increase your speed by 10 meters per second, you're going to need to accelerate for 10 seconds. So that takes us from 30 seconds to 40 seconds. And from that point, it continues at a constant speed. So until the end of motion, it's going to be traveling at 25 meters per second. Once I've got those points, I literally mark each one on the diagram and then join them up with straight lines. And that's my diagram. Ideally, I should label this with a T for the time axis and a V for the velocity axis. And then we get to the next part of the question. Show that in the first 40 seconds, car A travels 400 meters further than car B. So we look at the first 40 seconds. Remember, the distance covered is directly related to the displacement, and the displacement is the area underneath the velocity time graph. So for the first one, we look at the area under car A's graph, and that's a combination of this triangle at the beginning. We can use half base times height, and the rectangle that follows, which happens to be a square 30 by 30. So that gives us a total displacement of 1,050 meters. The car never travels backwards, so we don't need to worry about whether we're thinking of distance covered or displacement. They're traveling forwards along a straight road. For the next one, a little bit more complicated, but a very similar process. We've got the rectangle that corresponds to the constant speed section of the motion. And then we have this little section here, the next 10 seconds, where we're increasing our speed constantly from 15 to 25 at a nice regular rate. This is technically a trapezium, and you might remember the formula for a trapezium involves the average width multiplied by the height. This trapezium you might think of as being on its side. So the width it's talking about is the 15 and the 25. The average of those is 20. You can also imagine this as being bigger than a rectangle of height 15, but smaller than a rectangle of height 25. In fact, the average height of this rectangle, if you could turn it into a rectangle, would be 20. You can also think of chopping triangles off, or if you can't quite remember the trapezium formula, there's no problem with just breaking this apart still further into a rectangle on the bottom and a triangle on the top. But that should give us, when we work it all out, 650 meters. And there's no need to do very much verification with this one, because the question was, show that one car travels 400 meters further than the other, and these two numbers are 400 meters apart. Therefore, we have car B traveling 400 meters further than car A. Now, for the next bit of the question, given that car A is 500 meters behind car B at the very beginning, at what value of t does car A catch up with car B? So for this, we need to use the fact that the displacement that we're measuring here is not a measure of exactly how far along the road the cars are. That depends on where they begin. So up until this point, you were probably assuming implicitly, like I was, that the cars both started from the same point at the same time. And although the motion begins at the same moment in time, it does not begin at the same point in space. But that doesn't matter. What we've worked out so far doesn't tell us how far along the road they are. It tells us how far they have moved from their starting position. So it's a relative displacement. And it is true to say that car A has traveled further than car B, but we don't know if it's ahead of car B because we don't know where they started. It's equivalent to saying one person gets paid £1,050, someone else gets paid £650, but we don't know who has the most money at this point because we don't know who had the most money before and how much more. Now, it turns out car A was already behind car B by 500 meters. So the fact that it's covered 400 more in the first 40 seconds doesn't make it quite catch up with the other car, but it does reduce the distance between them. So in order to catch up, we're going to need to work out at which point in time car A has covered a displacement which is 500 meters greater than that of car B. And we know that's going to happen after 40 seconds because at 40 seconds, there's a gap of 400 meters between the displacements, and we need a gap of 500. We need car A to travel at its slightly greater speed for a little bit longer before it covers the additional 100 meters. And you could, if you wanted, just work with that 100 meters additional displacement and say, how long does this faster car have to travel at 5 meters per second faster than the other one before it's covered an additional 100 meters? And that's probably the most efficient way to do this. But it's not essential to find the cleverest, most efficient way, and it's very rarely the case that that happens straight away. So I'm going to do this from scratch, but I can use the fact that I've already got the displacement for the first 40 seconds. So I'm going to use the fact that capital T, wherever it is, and this is just an arbitrary point I've chosen, which turns out not to be correct, but it's accurate in the sense that it's greater than 40. So I've got a sense of which bit of the graph I'm interested in. Well, the extra part that we're adding on is going to be the speed of the car, which is 30, multiplied by the time that it's been traveling since the 40-second mark. And that's where T minus 40 comes in. That's the gap between the 40 seconds, because we've already calculated the displacement up to that point, and this new point in time. And we can work that out and simplify it and get an expression for the total displacement of car A in terms of capital T. We do the same kind of thing with car B. We've already got the displacement up to 40 seconds. Then at a speed of 25 for the remaining seconds between 40 and T gives us 25T minus 350. Then we've got to be careful we get the next bit the right way round. We want car A to have traveled 500 meters further than car B because it needs to catch up, and it started out 500 meters behind. So we put SA equals SB plus 500, and we rearrange and simplify. We get T equals 60. It seems like a reasonable number. And if you think about it, over the course of 20 seconds, if one car is traveling 5 meters a second faster than another one, 20 seconds of that difference in speeds is going to give you 20 times 5, 100 meters difference in displacement. You can check directly with each one, and go back and verify with your formulas to see that the actual distances covered make sense, but also just looking at the graph and seeing if your numbers are the kind of numbers you're expecting is a good idea. If you make a mistake here and get a value of T that's less than 40, it might mean that what you've got is a minus 500 instead of a plus 500, and therefore the calculation is giving you a number that doesn't make sense within the context. And that was questions 7 and 8.